Well, good morning. I'm Bill Roach, and I'm the chair of the Environment Committee, and we're doing a joint presentation. This is one of with the Let's Talk Science Committee, and thank you for allowing us to do this in this space. And this is the actually the third in a series of four talks that the King County folks are providing for us on various aspects of water quality in Puget Sound. And today we're going to be listening to Curtis DeGasperi, who is the had 23 years with King County, and before that we started in a very interesting way learning about his craft in the Peace Corps in Guatemala, and he has quite a story to tell there. I'm not asking him to tell here. Mainly, his focus today is on sediments and the story they tell in terms of our Lake Washington. He is a graduate, had a master's degree, a master's in science at the University of Washington, and has been with the county for 23 years. So, Curtis,
all right,
welcome.
All right, thank you. All right. Well, thanks for coming. And I'm going to be talking about what sediment coring studies can tell us about long-term water quality trends, specifically in Lake Washington. But first, I thought maybe I would just talk a little bit about water quality monitoring and what we can learn from water quality monitoring, and maybe sort of try to touch on some of the limitations and why I'm trying to promote this idea of using sediment cores to also look at long-term water quality trends. And so I want to go back to tell a story about Dr. Tommy Edmondson, who is pictured there in this slide. And he's a professor of zoology at the University of Washington. He passed away in, I think, 2000. But he came to the University of Washington in the 1940s. He'd studied at Yale under a Professor G. Evelyn Hutchinson, who was one of the, I guess, giants of the limnology field. He published a multi-volume treatise called the Treatise on Limnology. He was also the kind of person that, would write art history books and all that kind of stuff. So Dr. Edmondson was a pretty amazing fellow. And eventually he had a grad student one day that was out sailing on Lake Washington in like 1954, I think, roughly. And he noticed the water looked a little odd, and he was studying phytoplankton and zooplankton, and so he recognized that maybe something was interesting there, and so he had to pour out some beer. He had a beer bottle. He filled up the bottle with water and took it back to the lab, and they looked under the microscope, and they saw this algae, Oscillatoria rubescens, that because they communicate with people, they were internationally involved scientists talking to people around the world, and they had been at conferences, and they recognized that this was a species of algae that had been seen in Lake Zurich and was connected to nutrient pollution in Lake Zurich. And so they recognized that there looked like there were some initial signs of problems, and the reason for that was that in the 1940s, Seattle began to expand over the lake. We had floating bridges and things being constructed, and and World War II was created a booming economy here and brought lots of people to the area. And those communities, they built wastewater treatment plants to serve those communities, and those were secondary wastewater treatment plants. Which is sort of, up until recent times, sort of the state of the art in wastewater treatment. And those plants began construction in the 1940s, and that sounds great, except that the thing about secondary wastewater treatment is that it's designed to reduce the biological oxygen demand of the wastewater. And so the process is basically a bacterial process that decomposes our organic matter and converts it into carbon dioxide and water and soluble nutrients. And so they were basically doing a great job of fertilizing the lake. And Dr. Edmondson recognized this, and so did some engineering people at the University of Washington. And so in 1955 or 56, they published a paper and described this problem. And that generated some civic interest in doing something about the problem. And so I don't know if you've heard about a metro, but there was some pushback, but a measure was put on the ballot, and it did eventually pass in 1958 that created something called Metro, a metropolitan district that would create a regional wastewater treatment system. So they diverted wastewater from Lake Washington and also Lake Sammamish and to new treatment plants on Puget Sound. And so Dr. Edmondson, he definitely portrayed himself as being an objective scientist, that he wasn't promoting this idea, but he was providing scientific information. And so he has this great book called The Uses of Ecology. Highly recommend that. And so he recognized that they were doing a natural experiment, that he could, because it was actually quite controversial that phosphorus causes algae problems, algae to grow, and was the reason why this was happening across the world, and also questions about phosphorus in laundry detergents. People had introduced phosphorus. It was very effective at making our clothes nice and clean and bright, and so the detergent industry was pushing back on this. And so this was a great natural experiment. And so he started a systematic monitoring program in the 1960s, and he hired technicians. So he describes how he thought about this, that he wasn't just going to use graduate students to do this. He was going to hire people and keep them on long term, so that the measurements, the work that was being done would be consistent over time, so we get a good data set. And so what we can see is that here's the data through the 1980 or so. And he measured a lot of other things, but Secchi transparency is a measure of the transparency of the lake. And so as the sewage effluent reached its peak, the transparency of the lake became quite low, like a meter. You could only see this disk down to a meter in the water column in the lake. And then after the sewage was diverted, you could see that the transparency here at this point came back to a transparency that was equivalent to what it was in the 1950s, because there were some measurements that this graduate student and Edmondson and other folks had made back then. And then there's this nice, even larger increase in the transparency of the lake. And he'd also collected a lot of data on phytoplankton and zooplankton. He was collecting information on nutrients, and he was able to sort of weave a story about how this is due to an increase in something called Daphnia, water flea, that would, once the sewage was removed, and that oscillatoria, which interferes with the feeding mechanisms of this water flea, and a fish called the longfin smelt that was more successful because of revetments that were built on the Cedar River, that the Daphnia became dominant in the lake, and they cleaned the lake up even further and made it even more transparent. So this is something, the story that is, if you're in the field, this is like the gold standard of monitoring and collecting information to tell these stories. But it was also, at the end, very hard for him to find funding to keep this going. So I don't think I'll say much more about that. So there's Metro, and so Metro's been formed in 1958, and Dr. Edmondson's doing his work, and so Metro is mostly a wastewater treatment, and now Metro was merged with King County in 1994, but they were mostly, it was supposed to be a wastewater treatment system, and so there was always a little pushback when they also ranged into water quality monitoring. But back in the late 70s and 1980s, there was people were starting to get concerned about non-point source pollution, stormwater runoff and things like that. And so there was a federal program that provided funds, it's called the Section 208 program, that, and they recognized Metro instead of King County. They said, Metro, you're gonna get this money and you're gonna do some good work with it and do basin planning. And so they started some monitoring, but it wasn't led or it wasn't designed by one person like Dr. Edmondson, and and so it kind of had fits and starts, and not really a coherent program with kind of a question like we're running an experiment and let's follow what's happening. And so, I think the first metro study that I'm aware of is Lake Sammamish, 1964 and 1965. They realized, well, if this is happening in Lake Washington, maybe we should look at Lake Sammamish. And they said, oh, wow, I think the same thing's happening here. Issaquah has a wastewater treatment plant. There's also a dairy processing facility that discharges wastewater into Issaquah Creek and eventually into the lake. So let's monitor here, but only for 2 years. And then University of Washington, another group, civil engineering group led by Gene Welch, started studying the lake from like 1970 to 1975, and then monitoring kind of stopped again. Lake Union, the earliest data we have for Lake Union, because Lake Union is kind of another sort of thing on its own, that it was getting combined sewer overflows, the mixture of stormwater and sewage that happens in Seattle, because we have a combined system that takes most of our stormwater to the treatment plant and takes care of it, but in a big rainstorm that can overflow, and a lot of that happens in Lake Union. So they did some studies, and they were monitoring Lake Union back in the 60s. We don't actually have the data in our digital laboratory information system for that, but we do have data going back to 1974. And then Lake Washington, Edmondson was studying a site. He did most of this work at one station off of Madison Park. But we started monitoring in 1981, but not at the station that would be the Madison Park station, this station right here, but at these stations, one just off of Kenmore at the mouth of Sammamish River, and another one in Juanita Bay. Why they started there, I don't know. There's not a lot of records that even explain, sometimes why these stations were picked and why we monitor there. But eventually, we started monitoring a lot of stations. So you see all these pins, and so that was our program in 2008. We were sampling these places, twice a month between say March and November, and once a month during the winter. But we had some budget cuts, and the program's been reduced now to basically where these red pins are. But it's still a pretty extensive network, and still a lot larger than what Dr. Edmondson was doing on Lake Washington. And part of the reason for all these sites along the edge of the Lake Washington and Lake Sammamish that we no longer sample was that there was again a concern in the late 70s and early 80s about stormwater pollution and how that might be affecting the lake. So the idea maybe was that we would see more stormwater impacts at the shoreline, but it is kind of obvious that if you put a site at the mouth of a creek, not in the middle of the lake, that it's going to look different and probably be affected by something coming out of the creek. I'm not sure how informative that was, so I think it was a good idea that we kind of stopped doing that. And so those limitations aside, we've learned a lot, mostly about nutrients, algae, and temperature. Temperature basically going up with climate change. And interestingly enough, that nutrients and algae remaining fairly stable or maybe even declining in spite of all the population growth in the region. And so here's some of our recent reports and even a published paper. And we're hoping to get some publications out on that. And then I just want to mention that Dr. Edmondson was pretty good about, if they're going to change the instrument, we've got to do a lot of side-by-side measurements for a long period of time until I'm satisfied that we can make some crosswalk between these or that we're getting the same numbers. We may have not have been as good about that in the past. So we do, but laboratory methods have to improve. Instruments get old and they need to be replaced. And so we have developed some correction factors for some of those laboratory changes. But even with those adjustments, you can see in this graph, here's the University of Washington phosphorus data, and there's that period of wastewater input. And then here's our data, and I can't prove it beyond a shadow of a doubt, but physically, it's pretty much impossible to generate that much phosphorus in the middle of the lake without all those wastewater plants still discharging to the lake. So the data here are pretty suspect in my mind. And Why that happened, I don't know, but just to suggest that with our monitoring programs, there's always this problem with improving methods and instrument changes. So we get to the sediment core story. So I'm going to suggest that we get longer, because we can go back even further than the 1960s with sediment cores, and we get maybe more consistent data sets with perhaps less effort. And so just to, I guess I didn't make this point strong enough before, but I think we're mostly often wondering whether things are getting better or getting worse over time. So that's why we do this long-term monitoring. And we probably also wonder if our management actions are having any effect. So I think lake sediments, they provide a valuable record of the response of the lake to pollution inputs, because they are ultimately the repository of inputs from the watershed, but also from the airshed, right? So there's stuff raining down on the landscape and onto the surface of the lake. And the sediments also record the response of the lake to nutrient inputs that I've discussed. In lakes, an increase of inputs of phosphorus, otherwise known as eutrophication, can cause an increase in algae and alter the types of algae that are present in the lake, that oscillatory that appeared. And so just to explain that when we collect a sediment core from a deep, undisturbed location of the lake, we get a continuous record of inputs to the lake and the response of the lake to those inputs. We used a box core to collect this sediment core. They cause minimal disturbance of the surface sediment, and they provide a lot of sediment for various laboratory analyses. And I'm going to explain what a box core is. It's basically a long stainless rectangular box that's weighted at the top, right there, and articulated jaws at the bottom. That they're open when the core is lowered into the sediment. So the jaws close, and the coring device is winched up and onto what is called a sectioning table. And then inside the box coring device is a plexiglass sleeve that I hope you can see in this photo. And the next step is to remove the device and begin to extrude the core using this calibrated wheel on the bottom, at the bottom here in this photo. And then there's a plate that pushes the core up through the plexiglass box, and that's this plate right here. That wheel turns a crank and drives this up and presses this sediment up. And so now the surface sediment is at the top of the plexiglass sleeve. And so now the tricky part, it's slicing the core at 1 centimeter intervals. And the trickiest part is this, there's a lot of there's a lot of water in that first section. So it's the device could probably be built there'd probably be some improvements that could be made, but basically you wedge that little stainless steel plate into that little crack there, because this is just pressed onto the top of the box, and slice that off. And as you get deeper and deeper in the core, it gets easier and easier. All right, so note that we took care to remove the sediment touching the sides of the core to minimize the smearing effect of the core entering the sediment, and when it's pressed up through the sleeve for sectioning. So the Lake Washington watershed covers over 500 square miles and encompasses 30 cities, including Bellevue and a portion of Seattle, and almost 20% of Lake Washington's population. And here you can see the sort of a graph of the population growth in the basin since the 1960s, going steadily up to now we're at about 1.4 million people in this drainage area. So the Lake Washington airshed is not as well defined as the watershed, and it certainly includes pollution sources as far away as Tacoma. So there's Lake Washington. We're down here in Tacoma, and here we're looking. This is represented. This airshed, maybe in this case, is represented by the soil arsenic footprint that resulted from 100 years of operation of the Tacoma smelter that closed in 1986. Initially, it was a lead smelter, but switched to smelting copper after 1913. And the smelter smokestack was a regional source of acid rain, arsenic, cadmium, copper, lead, mercury, and antimony contamination. And there are acid rain studies where they could see this footprint of this of the emissions from the Tacoma smelter all the way up in British Columbia. So other air pollution sources in the Lake Washington airshed include so-called mobile sources, like gas and diesel combustion exhaust from cars, trucks, and buses that serve the transportation needs of about 4 million people in the central Puget Sound area, and stationary regional industrial sources like cement plants. Maybe seen those in the Duwamish, the steel plant, and power plants. So our study questions were relatively simple. I mentioned right now this is kind of a pilot study. What can the collection and analysis of sediment core from Lake Washington tell us about its history of eutrophication and recovery? And recall again that eutrophication is simply an increase in nutrient input, particularly phosphorus, to the lake. And the second question was, what could a sediment core tell us about long-term trends and recovery rates due to historical trace metal and PCB inputs? And PCBs, or polychlorinated biphenyls, are chlorinated organic compounds that are highly toxic. And I'll talk more about PCBs later. So Lake Washington, as I've already mentioned, is a well-documented history of eutrophication and recovery following diversion of treated wastewater inputs containing phosphorus in the 1960s. And as I mentioned, much of that work was done by Dr. Edmondson at the University of Washington. And in addition to water quality monitoring data, there have also been previous sediment coring studies. So conducting a pilot study in this well-studied lake meant that there would be a wealth of independent data that we could use to validate our results. And Lake Washington was selected for the pilot study because we could compare our results to earlier studies and demonstrate the reliability of the field and laboratory methods that we used, and build on the previous wealth of knowledge about the lake. And I'll emphasize that this was a pilot study, an attempt to demonstrate that these types of studies produce useful and reliable long-term trend data, and maybe also just say that you could see that there were previous studies done with sediment coring in Lake Washington. This was something that was pretty common back in the 1970s and early 80s. There were scientists at the University of Washington that pioneered some of the dating methods. They were doing the same kind of work in Puget Sound, and I could probably I won't go into it, but it's I don't know, interesting. Unfortunate that this tool has kind of lost some of its. People aren't as interested in it anymore. Although the Department of Ecology is one group that is interested in it, and that's why they have the sediment core that we borrowed, and they do have a program that uses sediment coring to look at trends in lakes across the state. So we collected a 40-centimeter core in September of 2020, and this project required a great deal of collaboration. So that included core dating that was done by the Science Museum of Minnesota. Fossil algal pigments were analyzed by a lab at the University of Alberta in Canada, and carbon and nitrogen and their stable isotopes were analyzed by a laboratory at Washington State University. And box core sectioning equipment and field assistance was provided by the Department of Ecology. And our King County Environmental Lab contributed field support and laboratory analyses, including analysis for sediment phosphorus, fossil cyanotoxins, the toxins associated with blue-green algae or blue-green bacteria, and metals and PCBs. So we collected our core from a location north of the SR 520 bridge. This location was also cored by the USGS in 1998. And we chose this location not only because there was a comprehensive data set from the USGS that we could compare to, but their dating results indicated that a 40 centimeter core would include sediments dating back before the mid 1800s, a time prior to significant human alteration of the landscape and the lake. Previous measured sedimentation rates at other locations, for example, location off Madison Park, this black dot, just south of the SR 520 bridge, or at a location in the southern end of the lake, indicated that much longer cores would be needed to ensure we'd include pre-development sediment in our core. And the core we had available was only 40 centimeters long, so I would have had to find a bigger core and would require a little bit more work, perhaps. Note there's a lot of other historical monitoring locations. And in the presentation, I'll show you data from the USGS core, as well as data from other cores that will demonstrate that similar results could be attained by coring other locations, and that a single core can be representative of the history of the lake as well as water and air inputs to the lake. And probably just most of the comparisons are going to be to a Barnes core just north of the SR 520 bridge, and the USGS core, and this core at the southern end of the lake that was collected by the Department of Ecology. So this annotated photo illustrates some estimated dates at different depths in the core. And so even though this looks like a relatively homogeneous sediment, that I'll argue that fine slices define very relatively specific points in time. And just for some perspective, plats were filed for the town of Seattle in 1853. Seattle was incorporated as a city in 1869. The Tacoma smelter begins operating in 1890. Most of the lowland forests around the lake were cut by 1900. Expansion of the road network began with the rise of the automobile after 1900. Commercial production and use of PCBs began in the 1920s. 1941 marked the first secondary wastewater treatment plant discharge to Lake Washington. Secondary wastewater inputs to the lake peaked in 1963, and then the Metro Wastewater Diversion Project diverted all that wastewater by 1968. And PCB production and environmental releases peaked in about 1970 and declined rapidly thereafter due to a production phase-out and ban in 1979. And gradual reduction in the use of lead in gasoline and introduction of unleaded gasoline in the 1970s. And then the Tacoma smelter ceases operation in 1986. And then just want to mention that since the 1970s, there's been a lot of environmental regulations have been ushered in. The Clean Air Act of 1970, Clean Water Act of 1972, CERCLA or Superfund in 1980, and then of course similar state and local regulations, including a lot of emphasis on stormwater management. So the regional wastewater system, the benefit of that, I believe, is that they replaced existing wherever the system expanded to. So initially, it was confined to a certain service area, mostly around Lake Washington, Lake Sammamish. So they're replacing septic systems to some extent. They're also capturing the wastewater from the existing wastewater treatment plants, but also beginning to service places that have been served by septic systems. And that's probably been a benefit regionally. For example, the city of Sammamish was incorporated in the 1980s, and so that would have been brought online into the sewer system. But there's still, people are still building homes, and septic systems are still being put in, and so that is a source of nutrients to the lakes and streams.
Black Diamond, Lake
Right, right, yeah. Beaver Lake up on the Sammamish Plateau still has septic systems. With respect to results, I'll just start with the change in sediment accumulation over time. And so time's on the bottom axis here, and the mass accumulation rate of sediment on the vertical axis. And probably contrary to your expectations, sediment input to the lake did not increase substantially during the period of early deforestation, before 1900. Of course, we don't have a really good picture. There's some issues with this calculation at the beginning and end of the time series, but I'm going to argue that this increase was associated primarily with the expansion of the initial road network, which wasn't paved. It was an unpaved network, and dirt roads are sort of notorious for being great at delivering sediment to streams and lakes. And then it peaked in the 1940s and then began to decline in the 1960s. And I'll argue that the decline was associated with a reduction in soil erosion due to reforestation and better land management practices. So first, quick orientation to these graphs. The vertical axis shows the depth in the core from surface to bottom, and the horizontal axis is the ratio or concentration of each parameter. And this is a conventional way of plotting sediment core data. And lower to higher ratios from left to right on the horizontal axis. And not every parameter was measured in previous studies, but the data for, I think we can see like phosphorus location at two different locations is very similar, and this from this much older core. Similar story for nitrogen and for carbon. And so similar results from different locations indicate our core is representative of general lake and watershed airshed inputs. And again, now we've got the dates on the vertical axis and the concentration of metals on the horizontal axis. And with a few minor exceptions, the metals data were also very consistent with previous studies. Arsenic's a little bit trickier. Maybe there's some issues with the historical data. Chromium, in this case, for this one core, there's a problem with the recovery of the metal in their analysis, perhaps. But some of these other metals, mercury, nickel, zinc, look really good compared to historical data. So again, similar results from different locations indicate that our core was representative of overall lake conditions and watershed airshed inputs. Here's the algal pigments. The fossil algal pigments track the eutrophication and recovery period very well. And a statistical analysis, a cluster analysis of the pigment concentrations identified 3 zones, with this middle zone capturing the period of peak wastewater inputs and recovery from 1951 to 1975. And I'll just highlight the ones that really captured that peak and then transition from pre to post eutrophication. Aloxanthin is a marker for a pigment for cryptophytes. Diatoxanthin is a marker pigment for diatoms or brown algae. Lutein is a marker for green algae. Mixoxanthophyll is a marker for blue-green algae. And then total chlorophyll is basically an estimate of the sort of like the total biomass of the algae. Here I'm showing you back to showing the time on the horizontal axis and concentration on the vertical axis. And this is a subset of the algal pigment data and comparing it to long-term summer, June through September, average lake surface total phosphorus data on the top graph. And you can see the clear response of the sediment pigments to increasing and then decreasing lake phosphorus inputs. And here I'm using some of that University of Washington phosphorus data and combining it with our more recent data. And I've translated those diatoxanthin, so this is the diatom time series, the green algae lutein time series, the myxoxanthophyll time series for blue-greens. And then we see the microcystins. This is from an enzyme assay, and the toxins associated with blue-green algae. And you can see that although we weren't monitoring the water for algal toxins back in the 1960s, this suggests that they were elevated during the period of eutrophication. And we're not seeing them much in the newer sediment. So I received some inspiration from a Puget Sound coring study that was done in the 2000s that calculated recovery rates of lead and copper in Puget Sound sediment cores due to declining inputs from air, wastewater, and watershed inputs. And they predicted the point in the future when concentrations would reach background levels. In the case of their two cores from the Central Basin of Puget Sound, that was for lead and copper. That was predicted to occur sometime later this century. So there's no widely accepted definition of the term trace metal. They're generally considered to be metals that are naturally found in relatively small amounts that are often enriched in the environment due to their refinement and use by humans. We've got time on the horizontal axis, concentration on the vertical axis, and then these dashed lines are the estimated background concentrations based on the concentration of the metals in that pre-1860 sediment from our core. And using a statistical technique called segmented regression, it appears that lake inputs of cadmium, chromium, lead, mercury, and nickel are all declining. They had this initial increase, but they've all started to decline, and lead and mercury may reach background before 2050. While cadmium, chromium, and nickel may reach background closer to mid-century. And just a disclaimer, these projections are, past performance is no guarantee of future returns, if you've ever heard that phrase. It's just, forecast based on the available data. So that's some good news, but the news for copper and zinc is that the concentrations of these metals remain well above background concentrations, and the inputs appear to be holding steady in the case of copper, or even increasing, it looks like the case for zinc. And note that a significant source of these metals is from auto and truck brake and tire wear. So maybe reason for that might be partly due to that. And these findings support the inclusion of copper and zinc in many of our recent stormwater retrofit studies. They seem to always pop up as being sort of the things that, metals anyway, that seem to be elevated in stormwater runoff primarily. And so we've been focusing our management and monitoring and management efforts on these two metals. So now I'm going to move on to PCBs, or polychlorinated biphenyls, and basically time on the horizontal axis, concentration or release in to the environment on these other axes. But so the top graph is the sediment PCB concentration over time, and then the next graph is the annual PCB production estimate over time. And we don't have a full picture of that, but we do have some good data for that. And then the annual PCB releases to the environment. And you can see that that the PCB concentrations in the core track very well with the increase in production, and then the phase out and ban of production and environmental releases of PCBs. And PCBs were voluntarily phased out of production in the 1970s, and manufacture of most of the uses were banned in 1979 in the U.S. But the sale and production of PCBs has been some PCBs do remain in use in insulation, fluid, in transformers and capacitors, and in building paints, caulks, and sealants. So there's still some PCBs in place in our built environment. So the Lake Washington sediment PCB concentrations track closely the rise, peak, and fall of US PCB production and estimated releases. And as a result of the production and phase out and bans on the use of the PCBs in 1970s, it's declined pretty dramatically. So this top figure illustrates the 2020 sediment PCB core results in comparison to that previous study by ecology at the southern end of the lake. And you can see they match very closely. And then the lower figure, this figure here, shows the segmented regression results for those two PCB cores, and the data from those two cores. And it shows that the sediment PCB levels decreased rapidly initially from the 1970s to about 1980, and then they've been declining more slowly since about 1980. But it looks like they might reach less than detectable levels before 2050. And again, past performance is no guarantee of future returns, but that's what the data are telling us. And detectable levels, I mean that the current laboratory detection limits. So it doesn't necessarily mean that PCBs have gone away and that they're not a problem. There is a fish consumption advisory for fish in Lake Washington as a result of PCB contamination. Recall that Tacoma smelter footprint. The arsenic story is a bit complicated. The results from a previous coring study are similar. Both cores have a peak from the smelter inputs, but there's another peak in both cores at the surface. And this is due to the influence of low oxygen in the lake sediments, which allows arsenic to become dissolved and diffuse upward through the sediments. And low oxygen is normal for these deep, relatively organic sediments, although climate change could cause oxygen levels to decline further in the future. Lake oxygen is something we watch very closely, and we haven't seen indications of any change yet, but we'll be keeping an eye on that. And then this graph was basically to make a comparison to some freshwater sediment cleanup screening levels that are kind of used as a guide to evaluate sediment for potential impacts on aquatic invertebrates. This isn't exactly these are very deep sediments. They aren't really the kind of invertebrates these guidelines are supposed to protect, but just to give a sense of how these are elevated concentrations, but what kind of harm might they have caused historically when they were elevated. And how do they compare to those levels now? You get a bit of a sense for that none of them ever exceeded those cleanup screening levels, except for this high concentration of arsenic, which kind of explained that's a result of the oxygen conditions in the sediment. And so in summary, and these are, just hit these points again, the sediment pigments were really effective in identifying the period of eutrophication and recovery. The microcystin results were also kind of interesting to be able to see that they were elevated historically, but at least in that enzyme assay, they don't appear to be elevated in today's sediments. We do see toxic algal blooms in Lake Washington once in a while, but they're not a chronic problem like they are in some other lakes around this area. These trace metals, cadmium, chromium, lead, mercury, and nickel, they peaked in the middle of last century, but they're all steadily declining, so that's good news. And the not so good news is the copper and zinc remain well above background levels. So we'll see what we can do about that. And the PCB inputs, they rapidly decreased after that production phase out and the regulatory actions of the 1970s, which means that we can change that story. There's possible to do things like that with other emerging organic contaminants. Arsenics peaked in the 1950s, but sediment arsenic concentrations remain high due to the chemistry of arsenic. And that's a condition that we see in other lakes around the region, especially small lakes closer to the smelter. Are more affected by arsenic contamination still. And some recommendations. Hope that somebody will do this study again, maybe in 2030 or so, and reevaluate the findings of this study. I mean, science is supposed to, we're supposed to, be checking everybody's work, and of course, even if nobody checks this right now, that somebody can go back and revisit this and see if anything's changed. And sediment environmental DNA is a very interesting thing that be interested in looking at, and trying to find people that will be interested in helping us look at this in the future. One of the questions might be sockeye. What would the history of some our kokanee? Maybe we could see the time history of fish in the lake. And then maybe you've heard a lot of news lately about the forever chemicals, per and polyfluoroalkyl substances, or PFASs. So Ecology has done some studies around the Lake Washington drainage and in surface sediments of the lake, but it might be interesting to look down in history and see, we've already had some phase outs and bans of some of these compounds, and so see if those measures are having an effect on sediment chemistry. And just point out that there's a report and data available online for this coring study. And thanks for your attention. And I'm not going to read all the names, but like I said, this is a big collaborative effort. A lot of people could have done this without them. And I'll leave it ready for questions. And just a quote from Dr. Edmondson.
Any questions? There's one at the back here.
Yes. Thank you. Thank you. Are there natural sources of PCBs, or are those the result of manufacturing of different things?
Yeah, I would imagine. I'm not super intimately familiar with the literature. I can imagine there's some combustion process, a forest fire that could produce one of their 208 congeners, different types of the PCB compounds but they're predominantly synthetic. Yeah, it requires a chemical process to make them.
Question here. How does climate change and rising sea levels affect lake quality?
So I guess luckily there's this lock and dam for Lake Washington, so it would take a lot of sea level rise before that's going to get overtopped. So I think that's it's probably not going to have much of an effect on Lake Washington. I imagine in British Columbia there are probably lakes that are potentially affected by that, but
there's no saltwater intrusion risk.
Yeah, no, that's true. So as it might exacerbate the saltwater intrusion problem. Most of that is usually confined to Lake Union. So Lake Union every year gets every summer into late fall, and occasionally when either there's been some mistake or happens at the locks that it has persisted through the winter, and that results in very low oxygen levels it probably exacerbates low oxygen levels in Lake Union. And occasionally that salt water has made it to Lake Washington. So that probably is something that we'll have to think about. I mean, I know that they've got also thinking about a lot of other changes at the locks to help fish passage. So I imagine that's something else that they have to work into the mix to think about. Yeah.
Gordon, I think, is next. Gordon?
I want to thank you for a very wonderful and informative talk, and it's nice to get some good news these days. But your first slide reminded me of something of maybe longer-term interest that might be worth recording. In the mid-1800s, the Vatican Navy was concerned about the water quality in the Mediterranean. Yes, the Vatican did have a navy, and they contacted a scientist in the Vatican to help them provide an indicator that they could use to monitor how the Mediterranean was doing. And they contacted a gentleman by the name of Pietro Antonio Secchi, and he developed something, and a little white disc that you would lower over the side of a boat, and when you could no longer see it, you recorded that depth. And so we now have about 140-year record of those for the Mediterranean. And of course, in his honor, we now call it the Secchi disc. And it turns out to have been one of the most wonderful environmental indicators ever invented. It's really simple. It tells you something. It's an indicator. It's not a diagnosticator. And it's still used. And we saw in your first slide, we're using the Secchi disc depth indicators to tell us something about what's going on in Lake Washington. And so here's a homage to probably the father of good environmental indicators, Pietro Antonio Secchi.
Mm-hmm. Yeah, thank you. Yeah. Yeah, and oddly, the State Department of Ecology in their marine monitoring program, they've actually dropped the use of the Secchi because it definitely is fraught with some. It's something that's hard to do well, or it takes some thinking to do well. But anyway.
During the from 1966 to 1972, I lived with my children in the Juanita Bay area. And you mentioned it earlier, that was a big test site at one point.
Mm-hmm.
I'm sure that was because it was a big beach area. It was a very popular,
right.
You could sit on the beach. And
Mm-hmm.
anyway, during that time, from day to day, week to week, month to month, during the summer, the beach is closed. And whether they were big beaches or little beaches all along that part of Lake Washington. And you either couldn't go on the beach at all, or you certainly couldn't go in the water. Can you tell me what data it was that was driving those closures?
Yeah, so that's always been a puzzle for me, because that's not quite the story that I told. The story I told was that there was a lot of algae, and that was the main concern. But you see the picture of the sign of the kids standing there, right, and as part of the metro pitch was that, there's these poor kids that are looking at the water and they can't go in, right? And so there is a sanitary part of the story, I think, that I haven't really looked into as thoroughly. But like I mentioned, there was, I guess I have to admit that these wastewater treatment plants, back in the 40s, certainly there were questions about how well they were operated. Right, they were operated by the local jurisdictions. That was the reason Metro wanted to take these over, was that to try to uniform, professionalize the treatment of the wastewater. And so I imagine that there were upsets that maybe, so I didn't mention, and I forgot this in another talk just recently, is that, so as part of this secondary wastewater, or any wastewater treatment process, even if it's only primary where they're just settling the waste, they'll disinfect it. They'll add chlorine, or nowadays they have other ozonation and a bunch of other techniques, but they disinfect the waste. But so sometimes you run out of chlorine, or the chlorinator doesn't work. So you have a period where bacteria are going to go into the water. That's why they would keep people out of the water, I presume, is that there's a break in a sewer line, or the chlorination system stopped working, or they didn't, or it was working, but you've got to really carefully. It's like dosing it, and then you have to have just the right amount of residual chlorine, and it's a complicated process. So I imagine that a lot of that was, and we have our combined sewer overflows, which there were many more of those, but only in Seattle. Seattle's the place that decided to do the cheap and easy early on combined system. Everybody else probably, I don't know if they learned from Seattle, but they did their sewer systems later, and so they did a separated system. But those would also be closing beaches more frequently back then.
You're persuading me to believe that there was no rhyme or reason to this closure of beaches.
I'd like to believe there was. I just, like I said, I've always been puzzled. I've always wondered, what.
I'm confused about the levels of copper and zinc that are going up. Is that due to some change in the environment? It clearly is not, or is it failed of being moved from the waste product? In other words, where is the problem?
Right. So
because those are unusual.
Yeah. So there's a number of sources, And, I guess honestly, we don't know. So I guess maybe another thing to admit is that, I think these sediment monitoring programs are like a core, helps us know what the history of copper was. But if we wanted to learn more, we would have to go back out and start monitoring a lot of streams and things for copper systematically to try to locate the sources, which is something that, we could do at a small scale, at least initially. But these, and maybe think about PCBs as well, is that we, even though we don't, if that was going up, then we would probably want to do some more monitoring in the water. But the coring kind of does a lot of this time trend analysis for us without having to do a lot of expensive field work. But in the case of copper, it's probably not the biggest only source, but breakware, they use copper in brakes nowadays, and they're trying to get a new brake product that has less or no copper in it. But there's something about the copper that they use that binds the material together. And so every time we're braking, little bits of particles of that brake comes off, and so does copper. And zinc is a compound that they use in trying to come up with the galvanized tires. What is it they do? Anyway, they vulcanize tires, right? So that's part of the process. So the tires have zinc in them. And of course, while we're driving along and we brake and we start, we're rubbing off bits of those particles. And roadway runoff isn't treated. It washes right into streams and rivers. And so that's one of the suspected sources of, but we also have galvanized fencing, rooftops that have zinc in them, copper downspouts. There's copper used in a bunch of compounds for, let's say, fungicides and things like that. So, but it's something it's kind of an open question. I mean, I think we need to look more into that.
Product and the waste is done, can that be removed from that current? Is there a current mechanism for doing it?
Well, for roadway runoff and any type of stormwater runoff, I mean, the bioinfiltration would probably capture that just fine. It's just that that's not something that's done at large scale yet. I mean, it's something that people are doing, but it's going to take sort of a long period of time of redeveloping roadways and urban areas to make that an effective treatment system for that source.
Okay, we have time for one more question. So, Jack?
I want to follow up on Dick's question about climate change. What would be the impact on the lake in terms of increasing water temperatures over time and the reduction in amount of inflow from snowpack?
Yeah, probably lots of things I won't be able to think of, but I mean, so let's start with the one about the reduction in inflow. So that's something that people are concerned about. That water's needed to operate the locks, to keep the salt water out, to keep the boats going in and out, at least to go out anyway. And so if that starts to decline, and not just the decline in inflow, but also evaporation from the surface of the lake, that's going to maybe cause some conflicts between fish and boating. And then the other question, so climate change, we already think we have seen, but it hasn't continued to trend towards this, but the summer surface temperatures are going up pretty dramatically. And it was at least some published papers back a while ago that the lake's stratifying earlier. So the thermal stratification starts earlier. It might even last longer, and so later into the fall. And that the algae kind of set up based on when the timing of that stratification is. So the bloom might occur earlier, and it's possible that other, like the zooplankton, the water fleas, do they know that that's happening? Can they adapt to that? And how will that affect the lake ecosystem is a big question. And then I guess also just that stronger thermal stratification, at least as it gets stronger and stronger and the lake gets warmer and warmer, we do expect the oxygen levels in the bottom of the lake to start to go down. I mean, there's plenty of oxygen in the bottom of the lake now. It doesn't go anoxic, but that's one thing that I think we would expect to see in the future.
Okay, I think we're going to need to close it right now. If you have some additional questions, if you come up for just a minute, I'm sure we can talk about that. But first of all, thank you very much, Curtis, for your talk.
Okay.
And to remind you that in 2 weeks, I believe 2 weeks, there will be the fourth in the series. It'll be on Puget Sound, issues around Puget Sound. I don't have the exact title, but we'll be writing it up in the next alert. And it's an interesting series of 4 that we've just tried. Thanks to Jack and Andy for really setting this up, this series. And it's the kind of thing I think we can learn a lot in terms of additional kinds of things where there's follow-on studies that we need to be considering as we work on informing ourselves about climate and other kinds of things. So thank you all very much.
Thanks.